name is Ines Aniceto, and she will tell us about analytic approaches to perturbation of strongly coupled Young plasma.
Thank you.
Go, Ines.
And thank you again for always inviting me to come here. This time is always amazing. It's like, it's my 1 week of summer. And today I'm very happy that I'm talking about something that I started nagging Alessandro and Giulio a long time ago with random questions of things that I didn't understand. And I had to wait until one of their students came to Southampton to join with my PhD student Alex to actually be able to do the project. So I'm very happy to have been able to do this. So this is about strongly coupled Young plasma, but of course this is very much about quasi-normal modes. So where did I enter and why did I care about this? This is just a very quick thing. We're talking about, meaning I've been studying a lot of different problems from the point of view of strongly correlated fluids, like trying to have toy models for heavy ion collisions. And so the idea is that after you get the collision, at some point there's an equilibration process, and macroscopically hydrodynamics starts to rule the system until forever, at least for us. It's a very short time, but it doesn't matter. So it's ruled by relativistic hydro. There's different approaches to it. There's kinetic theory. There's first order, second order relativistic hydro. But one of the things that you can think of is that you can consider, sorry, this is another thing. So basically, what are we studying? In fact, we're studying the energy momentum tensor. It obeys a conservation law, and what you want to study is basically the energy density, and you have an expanding plasma, so you have dissipative terms in the pi min u, and basically you have the original, the shear stress tensor, and then you have higher gradient corrections. You'd like to study the system, there's a few different ways. But of course, even with all the different models, all of them can be quite hard to tackle. And some of the things, we want the effective field theory, but of course that's governed by the microscopic theory behind the actual strongly coupled fluid. And so typically what we do, we know that when the hydrodynamics the relativistic hydrodynamics settles, you have basically approximately a perfect fluid. You have dissipative terms, but if you look very, very carefully and very hard, you actually have even something else, which a lot of people would say, like, there's no evidence of highly non-equilibrium initial conditions. But if you actually look hard, and from the point of view I'm talking about asymptotics and exponentially small terms, you would actually find them. But anyway, so typically we get we can even include extra symmetries in the system, so we can make the system simpler. And if you do that, so this is just to say that if you really make conformal symmetry and longitudinal, like invariance with the longitudinal boosts, you get just that basically you have a single function, the energy density that you want to solve. And you can now, one of the options, and that's the option that I will choose today, is to actually, okay, so how do I actually study the hydrodynamic evolution? What we do, we know that basically it's governed by the microscopic fluid. But in this case, we can assume that it's a coupled CFT, and we can use our methods of ADS CFT to calculate the perturbations, because we're talking about, we have hydrodynamics, we have the dissipative terms, and then we have these extra small things on top of it. And basically the idea is that beyond the very hydrodynamic case, what you have is that the linearized perturbations around some black hole solution gives you these dissipative terms. And then if you're even more careful, you can actually see that the non-hydrodynamic degrees of freedom are directly related to the quasi-normal modes. And that's basically the link. This is just to make it slightly more clear, but again, this is just very, very broad motivation, most of you would know, but just to kind of give you a hint of what I will be looking at. So I'm multi-equilibrium states, I have the black hole solution, that gives me basically the perfect fluid in some sense. We have perturbative, that's the perturbations, but then we have the exponentially decaying quasi-normal modes, which will give me the non-hydrodynamic degrees of freedom. So that's where I'm coming from. I started with strongly coupled Young-Mills plasma, and I finished with the fact that I'm calculating quasi-normal modes. That's what I'll be doing. So what I'm going to do, and I stole a lot of different things. The complex life of quasi-normal modes actually come from a paper that is called the quasi-normal of hydrodynamic modes, if I'm not mistaken. And I thought that it's a really nice. So that's the first thing we're going to do. Talk about like how one could do this at q equals 0, its connection formulas and complex, so the wave number finite. So typically this is done by truncating a certain complex curve, which gives rise to some to recursion relation, which you can solve. But the problem is, the big question that we have, especially for this problem, is when can you truncate and when can you not truncate? Does it always give accurate results? When does it stop giving accurate results? So you can always play the role of, let me truncate the curve, calculate my quasi-normal modes, and see what happens. But in fact, what we saw is that even though our problem does not exactly fall into the realm of the Seibel-Witten curve, we can make it such that it does, and we learn a lot from it. So that's the second part. And then from learning when we can use it and when we cannot, we actually try to say, let's go beyond that. And let's try and see that, okay, not finite Q, we can go to a completely different regime that in principle you could think not worthwhile. Like, let me go to large wave number. But what happens is that if I do that, and then I don't have my usual Frobenius expansion, the only thing that I can use are WKB solutions, because that's the type of solutions that you expect in that case. But then, because of asymptotics and because asymptotics works so well, you can actually bring your result all the way from infinity to 0. And in this case, I'm only talking about real Q. So I keep on saying Q because that's what I'll use. But I keep on saying, I'm only doing real wave number, so for the dispersion relation. But in principle, you could go to complex wave number as well. And that actually, as I'm going to show you very quickly, now that has some extra information if I did go beyond real Q. And finally, connecting the dots means connecting both perspectives. So the first thing, the complex life of quasi-normal modes. So yes, so we're studying linear perturbations of a particular type of helicity. These are the scalar perturbations. And basically this is on top of a black brane. These are dual to n equals 4 superring It's 2 superring mills. What is this in terms of the problem that I'm studying? This is just a boundary value problem, second order linear, Schrodinger-like. And the boundaries are basically the cyclical horizon and the conformal boundary. And that's basically, I want the solutions on both ends, and I need I need the solutions to agree with the boundary conditions on both ends, and then to use the connection formulas to match them. So that's exactly what I did. So if I find local solutions on both ends, and then analytically continue the solutions to match them, that's the connection problem. I should be able to find my quasi-normal modes that obey this boundary value problem. So what's the equation? What does it look like? It looks like this. I am not giving you where this comes from. I'm not giving you the metric and how to obtain the equation for the quasi-normal mode, but that's the equation that you get. You have two terms. Q is the modulus of the wave vector. That's the Q that I was mentioning. You have two terms on your potential. and this is what you look like. So S is just my quasi-normal mode frequency divided by Q, and Q is the magnitude of the wave vector, and basically my ADS boundary is at z equals 0, and the black hole horizon is at z equals 1. So I have my two boundary conditions, they are given by this. That's the properties I have. This is the problem I would like to solve. So why do I want to calculate omega of Q for general Q? Why would I even want to calculate omega of Q for complex Q? Well, actually, I think by now I've learned my lesson, and I hope that that you've learned yours as well. Often, even though we want to be in a certain regime that is the physical regime for whatever reason, but whatever is it, because we're trying to do a physical observable, still, often what happens in the analytic expression of my observable will have consequences within the realm of the physical domain. So it's quite important to try and understand the function as a whole, as an analytic function, in order to actually be able to take out all the information we need in the physical domain. In particular, what was seen, and this is a picture by a plot by Ben Withers in one of the papers, it's not this particular case, but it reflects exactly what I'm saying, is that actually by taking Q complex, what he found, meaning there's also Grozanov and Heller also did some of this, so what they found is that if you you're studying your hydro mode, you're studying like the first non-hydro mode, and you go in the complex Q plane, and you analyze it, you find that the omega of Q will have a branch cut. And at that branch cut, what happens is that there's a level crossing. Basically, the quasi-normal modes are labeled by an overtone, and they cross. So in order to continue the same, you need to cross the cut, continue somewhere else. So actually, like I said, there's information in complex Q beyond what we'd expect.
In the equation that you showed before, Q, small q is complex.
So Q is, well, in fact, Q is 1 over h bar. Think about it.
Okay.
But at the moment, we will take it as to be real for this work, but you can take it to be complex. In this plot that I'm showing, again, this particular plot is not exactly of this, meaning so Grozanov et al. Actually did similar plots, but they were uglier, and I didn't want to put them.
That's the Coin equation. It has 4 regular.
It's a regular point.
And what happens if omega is equal to 0 or q is infinity? Is it a hypergeometric function?
So omega is 0
Yeah.
and q infinity.
Or q infinity. So can you kill one of the? Okay.
So q infinity will
That's okay.
we'll keep q infinity we will take we don't take that, because what we're going to look for solutions that go as omega of q
Sure.
generally.
Yeah.
But or at least yes goes as 1. But in principle you can do that. But the point is, like, taking q infinity means that you're really killing off this is a singularly perturbed problem, right? Taking q to infinity means taking h bar exactly 0.
Right.
So you're changing the dynamics of you're killing the dynamics of the problem.
Okay. And in the plot you're showing us is the quasi-normal modes, and what
So
you're plotting is
the
all-
first, like omega 0 and omega 1, and how
so
in the complex
first
plane,
excited, and where are the overtones here?
0 and 1 are overtones.
Oh, so just that, it's
Yes.
not like all the overtones.
No, but they keep on having cuts
I
and
see,
crossing
they
each
cross
other,
each
so
other.
it's not just
I
this
see.
one. There's a whole, you could continue in principle.
Okay, I see, okay, thank you.
So another thing that would be interesting, and something that, for example, we'd be looking at right now, is that, meaning if you go to complex plane, actually the leading behavior in Q, you say, oh, omega of Q goes as Q. But sometimes if Q is imaginary, omega of Q might not go as Q. Even though if you go for Q real, it does. So something weird happens in between the two, for large Q, for example. So something happens. We need to understand the analytic structure. And that is one of the reasons why it's interesting to actually keep complex Q. And again, as I mentioned, even for real Q, it could happen that you have still what we're going to say Stokes phenomena or similar things, where something happens between infinity and zero, and it comes from the complex plane. So you might need extra information. So, finite Q. How can we solve the boundary value problem? We can rewrite the boundary value problem actually as an infinite curve, a complex curve. Basically, F is an infinite series of terms which are rational in both omega and Q. And because it's infinite, the only way to solve it is to truncate it. I mean, there's no other way. So, but definitely that function should give us, defines implicitly the omega of Q. So, but in practice we need to truncate, and natural questions arise. So, do higher truncations lead to better results? And clearly, if you have a higher truncation, that means that you have a higher polynomial to solve. That means that you're going to have a lot more terms. And it's not like you get another truncation and it's one more term. Typically, you get another truncation, you might get another overtone, but then you have a lot of spurious zeros of that polynomial. So, which ones are physical? How can I, from this huge polynomial, how can I track the physical results, the physical quasi-normal modes? And of course, I would like to calculate omega as an analytic function of Q. So let's start simple. Q equals 0. So Q equals 0, meaning this is not something that hasn't been done. This has been done before. So at Q equals 0, actually meaning it can really be expressed in continued fractions, and for Q equals 0, it can actually be seen that the truncation of the curve is the truncation of the continued fractions, is convergent, and you can really calculate the omegas at Q equals 0. So this was done by Starinets in 2002, and it works beautifully. But it can even be extended from what he's done, which is that you're not restricted to calculate your exact quasi-normal mode. You can calculate the Taylor series around Q equals 0. So you can calculate the derivatives of the quasi-normal mode around Q equals 0. It works exactly the same. It works beautifully, and you can calculate this Taylor series. In principle, you can take then the Padé approximant and find your branch cuts and all these things. This is a convergent function. So, okay, can we go beyond Q equals 0 and do the same exact thing, but now for Q0, somewhere else in the complex plane? Even real, sorry, not complex, but a different Q. And so we know that Q equals 0, everything converges. But can we learn about the convergence if I go to a different value of Q, to a different overtone N? So what happens in that case? And that is, with that question, sorry, I should have made more of a splash about that question. It's like, I want to go to finite Q, not just Q equals 0, I want to be able to do the same, but I want to make sure that basically I know that I can truncate my curve, that I will get accurate results, or if there is a point at which I can't, I want to figure out where that point is, or if I can get any information about it. And then we go to the second part, which is the lessons from Seibel-Witten. And what did they tell us about when not to truncate? So this is the same problem, rewritten in a different way. So this is basically a Hoyne equation, right? So regular for singularities, all the typical coefficients. So it's just a different variable. We've defined z, y in terms of z. And I've introduced now a t here. A t is a half. T is a half in my problem. I can't pretend that it's not, but let me for now ignore that t is a half and assume that I'm allowed to have a t. So I have the problem. This is all the coefficients. Here you can see that the quasi-normal mode shows up. This is S. S is the quasi-normal mode, basically. So it shows up in several terms. And we know, so we know the relations with the AGT correspondence. We know that we can relate this to a dual theory that is basically given by the quantum Seiwert-Witten curve with 4 fundamental hypermultiplets, and many the people in the audience, the organizers, have done connection formulas for this. I don't need to say, hopefully, where these they come from, but we can use that. So this is the connection formula between. So we care about, by the way, the boundary conditions are between y equals 0 and y equals t in here. And this is the connection formulas that relate the functions at t and at 0. I will repeat it, so it's up there now. So basically, what I want, so Ft is the instanton part of the Nekrasov-Chatishvili free energy. That's what shows up here. And which we know as a small t expansion. So let me now assume that I can have a small t expansion. So, so basically what I'm doing is choosing my connection formula between this 0 and this t.
Sorry, in the differential equation, did you have h bar still, or did you suppress it?
I have h bar, it's just written, sorry, here, here, and here. Q is 1 over h bar. But Q at the moment, I'm keeping it fixed. Like Q is fixed, there's no h bar.
Okay, so you still have these terms that go like q to the 0 sprinkled around.
It's
there.
it really is the exact same equation. It's just rewritten in such a way that I've written this, such that basically it's just so that you can see already where these a's show up here. But the equation is exactly the same.
In any case, h bar can always be absorbed, right?
But here there's no h bar. There's really no h bar. For the moment, there's no h bar. There will be, but as soon as I introduce h bar, which is 1 over q, then things change completely, because actually you can't employ the same methods. So basically, the connection formula does, in order to solve it, it assumes the instanton counting parameter t that is small. You expand it in small t, but the one good thing about having a small t is that it allows us to truncate this curve, to truncate the continued fractions that we get from our connection problem. So that's the one good thing about having small t. But in the end, we still need t equals a half. But again, let's keep on ignoring it for a bit longer. So solving for the frequencies, so this is just a change of variables. And this has, suddenly I forgot the name. When the expansion goes from -∞ to infinity.
Laurent series?
Huh?
Laurent
Floquet.
Floquet. Thank you. Sorry, I forgot a moment. So we're assuming a Floquet solution. We can do this for finite q. And the decays obey the 3-term recurrence. The A's, B's, and C's depend on those A0, AT, A infinity, etc. I'm not writing them here because it's just too big. But this is all, meaning all known. And for t small, we can obtain continued fractions. And basically, the continued fractions, what allows us is to calculate an expansion of this C, which, if I show you, it's basically 1 minus s squared. So my quasi-normal mode. So it's the C as a function of t. Okay, so that allows us, in principle, to calculate. So some of the things that you get is, of course, from, given that one of these solutions at t has to be killed, one of these gamma functions has to be 0. That's the quantization condition. Sorry. And the C is given by basically that as a t expansion. And basically, you can assure the convergence of the series in small t, and in principle safely truncate the continued fractions. So what we did is like, okay, let's do 12 instantons of my f of t. Solve for omega at an overtone n. in case this is solutions for n equals 2. And at the end, I have a convergent expression in t. Then let me set t equals a half and see how the results are. And what you find is that, for reasonably large, but not too large values of this is for just n equals 2, not too large values, they seem to agree, okay? But then you start increasing q, and it gets worse. Clearly, setting t equals a half is not cutting it. Can we pinpoint this? Can we analyze the function c of t? That's our first expansion that we calculated as an expansion of t. Can we analyze the convergence radius of c of t and perhaps try to find some extra information? You can. That's what it is. So this is different. So this here is what those I can't even count. 4 plots look like. So this is basically, this c of t is a convergent function. I'm just doing a Padé approximate, calculating the poles to see the nearest pole in principle is the radius of convergence. And okay, if I start with q and n small enough, this is the radius t equals a half, right? That's where I want to evaluate my function. The poles are far away, that's okay. But then, q equals 10, n equals 15, so the same q, but n equals 15, you see that the poles start accumulating at t equals a half.
Can you remind what is capital N?
Capital N is the overtone.
Okay.
Overtone.
Ines, did you find that, or you impose the dependence on the value of n as being a linear?
You find it as a solution. So you find omega n of t from the quantization condition. So the quantization condition is this. In order to solve it, you fix an n and you solve. And you can do n equals 1, n equals 2.
A and n, do you impose that relation, or?
So these, it's not obvious here, these depend on my quasi-normal mode. The C depends on my quasi-normal mode. This is an expansion that is known.
Yes.
And if you include the two, you can solve for omega of t for fixed values of n. So, okay, increasing n is getting us, like the t equals a half is the radius of convergence. What does this mean? It means that if I'm exactly at the radius of convergence, I will need infinite numbers of terms to make my series converge, right? So I'm starting to get in trouble. So q, again, okay, let me take n small and then q large. Oof, same thing happened. Something that is not obvious from here is that, of course, if I take q and n large, it seems that the same thing is problematic, so I'm still at the radius of convergence, but somehow, if both of them are large, I see a phenomenon that I don't really understand, which is that the result is actually better. So somehow, t equals a half is the radius, at the radius of convergence for large q and n, but somehow something happens when both of them, I increase both of them at the same time. So this is the summary that of what I've done so far. So t equals a half is reachable for small n and q. Truncation fails, clearly, because I'm at the radius of convergence. For q, either q or n large, but there's some regime of q of n both large where they sort of compete with each other. Again, another question that I haven't answered is that is still there is that like higher truncations, typically also of that curve, if you're solving for that curve, you get more spurious solutions. It doesn't tell me which one I should be tracking. So I still have the same questions. How do I get it then? If I want a q a bit larger or n a bit larger, how do I achieve that? Can I identify those physical frequencies? And can I just have an actual result for all ranges of q? And that's what we'll do, but with a completely different method. So we're going to use the so-called exact WKB method to solve this problem. So again, that's the same equation which I've written before. And now I'm going to want large Q. This, for large Q, as I mentioned, I now divide it by Q, and you can see that 1 over Q squared is basically the H bar, and this is a singularly perturbed problem. If it's a singularly perturbed problem, that means that I need to use WKB ansatz, that the Frobenius of low K or any of this type of solutions will not happen. So that's what I'm doing. It's actually originally called Liouville-Green ansatz from way before WKB. WKB were the people who actually applied it to the Schrödinger equation. So that's the ansatz that you get, and you assume that S is a whole expansion of Q. You can separate it into the odd terms and the even terms of Q, and you can rewrite your WKB solutions just in terms of the odd function, like this. So there's the integral of the exponential, there's a square root here, but the point being is that the leading order of the S odd comes in 1 over Q, so it's non-perturbative here. So that's the big difference between having a series solution or having that exponential. The rest is series, but that exponential makes the whole lot of difference. So I still have a boundary value problem, and I still want to do exactly the same thing as I mentioned before. I want to relate the basis of WKB solutions defined at z equals 0 and at z equals 1 through analytic continuation, and I want to be able to solve the boundary value problem to determine the omega. That's basically the same as saying that I want the quantization condition. So, but some things happen in this case. There's new things, and what are the new things? Stokes phenomena. So, through analytic continuation from one region to another, solutions actually that are asymptotic, like these solutions, can jump in value. They jump by something very, very, very small, right, by exponentially small terms, but they can jump. And the problem is, like, as soon as they jump by exponentially small terms, and then you continue, those exponentially small terms might be big, and then they contribute on the other boundary. So we need to be careful about this. When do they jump? They jump at Stokes lines. Basically, what are Stokes lines? Where one WKB solution is as big as it can get compared to the other. So exponentially enhanced compared to the other, the one that is the most exponentially suppressed. So it happens when the exponentials are purely real, and that means that you have conditions like this. You can write in the z-plane, complex z-plane, a Stokes graph, which is the collection of all these lines where this happens. And they usually emanate from, I'm not sure why I've written that J, that's a typo, from turning points, and the turning points, the important thing is that the turning points are typically singularities of the coefficients of this S odd. So this is our Stokes graph, just so that you see. There can also be branch cuts, I didn't mention this. So there were other large Q analyses being done before by Festucci and Liu in 2009, and then by Fuini, Juhelman, and Jaffe in 2016. And they calculated the leading order in the first correction. They sort of predicted what it could look like to the rest. And our objective is actually to determine the full quantization condition and calculate this systematically. So all perturbative, non-perturbative orders, everything. So what will the quantization condition depend on? It will depend on the WKB periods. Basically what I mean by that is I want to connect, and now I can't find here, but basically I want to connect 0 to a half. Or not to a half, sorry, 0 to 1. This is in the z variable again. But in order to do that, I need to kind of go and cross many of these lines to get from one to the other. But in order to do that, basically what you can see is that often those crossings, what will give you is basically contributions that you can redefine them in terms of periods around singular points or turning points.
Have you taken some degenerative here? Because I see there's a square root cut ending at 0, but in the cone equation, you didn't have.
So we've done something here. So what do you mean by the square?
What are these weekly lines? Is that their branch?
They're branch cuts.
So it's a branch cut for the square root, right?
Yes.
Well, why is it ending at 0? I thought you had a function at 0, like the double pole of the quadratic differential.
This is drawn for the leading order b0. When you take the square root, you'll have a 1 over z, which becomes a 1 over root z. Because it's just the leading order b0.
So because
Okay.
so the S odd, what you're taking really is just this integral, right?
Yes.
And but
But-
if you're approximating this, basically what you get is you
So you're
can
saying
get
that
1 over square root.
B0 has a first order pole?
Yes,
That's it.
but then you
Not
get
a second order.
It has a first order.
It's
For-
first
oh,
order.
okay.
The second order pole lives in b2.
Okay.
But you don't care about that to draw those.
No,
Stokes
for
graph.
the Stokes
So
graph, yeah,
here-
fine. Yep. Okay.
So basically, so you can redefine your connection problem through a basis of periods, and I'll show you what they are. And basically, this is quite systematic. So the quantization condition looks like this in terms of this alpha and beta period. So I have here the conditions. So there's this is one of the periods that goes around one of the branch cuts. This is the other period that goes on the other side with the branch cuts out. This allows you, meaning actually solving this, you can calculate like solutions to this systematically for large Q and N. You can calculate all orders. So this, because of this log, clearly you're going to have exponentials coming out. As it happens, alpha is beta in this case. So the two periods actually match together. So there's a symmetry and they're simpler. And the non-perturbative corrections are corrections in large N. This is what it looks like. You have my omega for overtone N and Q. You have to solve it for large N because there's asymptotics in N as well. And this is what it looks like. It has this weird powers of Q and N. And here you can already see why there was the fighting between Q and N. Because for N large and Q large, actually Q over N still remains the same. That was the reasoning for the good values in the other case. And each one of those terms actually will have a perturbative series, and it'll have a series of exponentially small terms, well, it depends on the direction, with some coefficients in N. So the series diverges in both N and Q. Both large N and large Q need to be resummed. And the resummation gives us an unambiguous value for the frequency. So what I was asking, what is my physical value for my frequency? You get a single one. So there's no lots of spurious solutions, there's just one.
Can I ask a very stupid question? Where is this? I mean, this looks like something nonlinear, right? Because you have infinitely many sectors. Hein is linear, right? So
No, the wave function solves a linear function.
because
Omega
you're
solves
doing
an
the-
implicit
it's
equation,
the-
right, which is the quantization condition.
Right.
The non-linearity that
Okay.
you're mentioning,
Okay.
but it isn't. Meaning you do. There is evidence that it comes from a linear equation, and the reason for that is that all the exponentially small terms are all related to each other.
Hmm.
So it's not just fully nonlinear. All bets are off.
Okay.
Here it's not like that. But still, the nonlinearity comes from the implicit equation.
Okay. Thanks.
So, what is my question now? Okay, I have my solution. I can resum it, but this is still large Q, large N. Can I actually obtain the other results that I was seeing before? And that's the last bit of my talk, which is let's connect the dots. So that is my equation for omega n of Q. I want to do a resummation, and what you do is like you choose some value of Q star and N, and what I would really, so the resummation gives me the frequency at some Q star and N finite, as long as they're not too small. Meaning, of course, I can't set, in the resummation procedure, I can't put Q equals 0 and hope for to give anything, because this is a Laplace transform, which has an exponential, and that exponential would be 0 if I did Q equals 0. So that's out of the question. But still, for a Q star, I can get my value of the omega, but more than that. I don't just get the value of the omega. I can actually, for each resummation, I can get the value of the omega, the value of the derivative at q star, the value of the second derivative at q star, and etc. So I can actually, from the large order, from that expression there, and resummed, maybe taking derivatives of it, what I can get is the Taylor series at different points in Q. So it was the same information that I was telling you that I could get from the truncated curve. So I fix my value q star and n. I do a resummation, and so the resummation is differentiation commute, and I can calculate derivatives of omega, and that means that I can calculate the Taylor series, at least some number of coefficients for that Taylor series, around the point q star. And what you can see here is that we did that for n equals 1 to 5, q star equals 5 in this case, and I calculated the first, these are the first 20 derivatives from the results, that from the large order, resummation, right? And you can see, like, if you look at L equals 0, which is, of course, I didn't add this, but it's the best one, clearly. So basically, this is the error, the relative error. You can't really see, I think this is 10 to the minus. So the first one is 10 to the minus 6 here, and then this is 0.01. And the quasi-normal mode itself is quite accurate, but then, of course, the higher derivatives I get less and less accurate because I would need more terms to actually get it as accurate. But basically, you can do that still, and you can get a fairly accurate result. But then, okay, what do? I calculated my Taylor series at q star. There's plenty of methods to do analytic continuation from that q star onwards. One of them, I mean, there's a few that we've mentioned, but one of them is just from the Taylor series, you can do a Pade approximant and just take your value to q equals 0, like as simple as possible. And if you do that, this is the results you get. Remember, we started, the only information we have is q infinity, right? And these are the results that you get from an analytic continuation to q equals 0. They're not great, but we're really pushing it, right? We're going at completely opposite directions here. So you can, meaning it's still fairly close. You agree 2 digits in general. Of course, the more ends you get, the less terms you need. So that's our meaning that's the origin of the errors there. Moreover, so this is just a comparison of the Pade continued quasi-normal mode and the direct results from the resummed expansion. You could also just do the resummed expansion at different values of q star. And that's the black dot that you get. You can go, this is q equals 1, q equals a half already starts diverging because, again, the resummation for very small q is going to be problematic because it's Laplace transform. But still, this blue line, the dashed line, is the Pade continuation from the Taylor series. The solid line is actually the opposite. From the information that I could get at q equals 0 from the truncated curve, kind of do a Pade approximant and continue it. So of course they agree at the beginning, but then that Pade approximant starts diverging. So this is definitely the one. So this is the point at which I calculated my Pade approximant. So this is q equals 4. And of course this is just the real and the imaginary. But you can see that it actually really gets you very accurate results. And one other thing that you could do with these things is that I was telling you from the truncated curve, you could just go to any finite q. However, well, not large enough. However, you need to have an input what the physical quasi-normal mode you're looking for is. And this easily gives you that input because it tells you that's the one that you're looking at. There's no spurious values. So then finally, just a brief summary. So we used the continued fractions and the Seibel-Witten curve perspective to actually understand the limitations of the finite q approach and truncating the continued fractions. Then we used exact WKB to actually calculate all perturbative, non-perturbative orders at both large Q and N. Obtain, with that and resum, we obtained the Taylor series at finite values of Q, and then did an analytic continuation to Q equals 0. So, other things that one can do with this, we can do different sectors. This was the scalar sector. We can try and understand the hydrodynamic mode in the shear sector. And also, meaning this was all real Q. In order to actually go to complex Q, the Stokes graphs change, so you need to be more careful, and there could be non-perturbative contributions in Q appearing, etc. So there are different problems that show up there. But in particular, if I did that, in principle, I could actually predict the cuts that they saw the level crossings in. Finally, beyond Hoyne, there's perturbations around other non-Hoyne equations, 5 singularities, for example, that one can try and do the exact same thing. And thank you.
Questions? Please.
Can you elaborate a bit more on what exactly you did in the exact WKB? I mean, you said you do exact WKB and you get some answer, but
basically what you really need to do is like you need to calculate these periods. Several terms of these periods. There's which means that you have to basically,
I mean, did you truncate this at some order, or did you really?
Absolutely.
Okay.
I won't be able to tell you how many. It was 70 terms in N. No, it was 100 for sums in N. Because it was a large N, large Q expansion, right? So it was 100 and something in N and about 70 in Q. That's about that. But basically, what I'm saying is that you really need to, meaning these all depend on Q, and as soon as you plug them into to here, they will depend in N. At least the leading order will have a full dependence on N. The subleading orders will have an implicit dependence on N based on the leading one, because they depend on the previous one. And you need to actually be, meaning there's ways of massaging things such that you don't have to do a full N and Q expansion. You can kind of try and simplify the process, but basically that's what you're doing. You're doing a large Q, large N, solving this equation.
Really by brute force, essentially.
But the brute force is just a calculation of the periods, and the periods are completely well defined.
Sure.
So you can really do this systematically. Meaning there's no.
Of course.
Okay, of course,
Yeah.
But still, meaning you can do this to 70 terms and.
No, I am not. I just wanted to.
But the brute force is just the fact that there's a lot of properties here and geometric properties. In particular, so for example, if you wanted to go to complex Q, the geometric properties are extremely important because these periods jump as well and change. But in terms of calculations, what you need is just to actually have a resummation in the end. So that's what you do.
Yeah, so the periods are well defined in exact WKB as long as you don't have saddle connections, right? If you have saddle connections. But I'm a bit surprised that I'm a bit surprised that you don't
This
have
is
them,
actually
because everything is real in your equation. There are going to be a real period, right?
But I'm hiding a lot of stuff.
Okay, good.
So this
so
is
you
actually.
You perturbed a little bit away.
This
from
is, if you want to put it that way, is complex N. You need to do a medium resummation in complex N.
Okay.
And that is, so N, the non-perturbative terms in N are actually, I didn't show what the results between not including them and including them, there's an obvious difference. But indeed, the actual, so there's bounded Stokes lines for real.
Yeah, no, there are saddles because everything is real in your equation. You have to perturb it.
So,
but the medium resummation, you say, gives
yes.
you the physical.
Yeah. So that's what I didn't say. Yeah.
Can I follow up on this? Can you say a bit more about why the medium resummation gives you the physical one?
Because you want to cancel the imaginary part of the result, basically. Well, but it's okay. Typically, the medium resummation gives you, because the medium resummation is what would give you the half jump at the Stokes line, which is what typically a function is evaluated unless you're doing very, as I'm concerned, weird mathematics. There are other resummations, there are other options, but the medium resumation is the one. So typically you'd say that no jump, full jump, you should have a half jump. A half jump doesn't mean calculate an average, right? Because you have a whole bunch of terms,
Sure.
and it's the half jump is the medium resummation definition. So that's why that would give you.
It's sort of,
At the
this is
Stokes
kind
line.
of this is almost like an aesthetic argument, right? Like, I mean, it looks like it looks like a sort of canonical choice, but
It's a canonical choice in a lot of cases, meaning the cases that I've seen it best justified actually are not justified via this type of things, is via errors, and I'm actually checking for special functions using hyperasymptotics, where they show really that there's a smooth, meaning there's like the Stokes smoothing, and there's a smooth value, and the value at the Stokes line is really the half. Is that enough? Maybe
I'll
not.
take it. Yeah,
But yes,
And
indeed.
actually, can I add something? So these graphs that are drawn, they're drawn with choice of n. So n's real, you perturb it, so it's slightly imaginary either way. Once you do that, that changes your graph. If you go to the quantization condition, this gives you a plus or minus. When you perturb n to slightly above the imaginary, slightly above the real, slightly below, this picks your resummation for you. And that also picks the plus minus sign in the quantization condition, and it's all consistent. There's no choice in this case.
so you check it and it gives you the correct result.
No. I have to pick the right resummation based on which n I started with.
I have to think about it a little bit. Thanks.
Curious. Please.
But just still on this, because sometimes with median resummation, what you're also doing is implicitly setting a lot of the time series parameters to 0, like the additional one, like the non-jumping part, effectively,
So the thing about this situation is that there's no unfixed transient.
there's not fixed.
It's an implicit equation for omega.
Oh, because once you're in the
There's
quantization
no-
condition, there's no.
No, so there's that doesn't.
That would
even
be for the wave function.
Yep,
For the
exactly.
for the this doesn't inherit in any way. Okay.
Exactly. The curiosity.
Yeah, the curiosity is you were talking about the level crossing
Yes.
for the spectrum. How can you see this level crossing?
From this
Yes,
perspective,
from this
I would have to go to
perspective.
complex Q.
Mhm.
Everything. This particular graph is real Q. So
Okay.
you would have, and the graph changes. So you can,
Mm.
but you need to do even a many. So this was this was more like a proof of concept, because when we started, we actually didn't quite know what we were doing, or meaning how. Basically, the point is not that we don't know about the periods. The point is that we don't know how to do things explicitly to calculate then values or something. So that.
But then,
And we kept Q real, but the original idea was actually, can we predict the points of those cuts if we go to complex Q? Because in principle, what would happen is that you go to complex Q, there's some Stokes line that you cross in Q, and because this is a Stokes lines in N, so you cross in Q, and then you turn on non-perturbative phenomena. What are branch points typically? These are points where all the exponentials start fighting each other and they make a zero or a pole or a branch point. So that would happen after the crossing of that Stokes line in Q, where you would have all the contributions then turning into branch nodes. But we haven't done that yet.
Okay.
Other questions? If not, we thank Ines again.